Welcome to the electronics class for December the 8th. As I said right before I turned on the recording here, we're going to start the class with a quiz, and you guys can expect that I'm going to do that pretty much every day from now on until the end of the term, well, at least until we take the state mandated test that we're going to have to take when we come back from the winter break. And so they're going to ask you a bunch of like schematic symbols and definitions and things like that. And I want to make sure you guys are prepared. So I'm going to give you a quiz right now. And the way that I want you to answer is by typing, type your answers into the chat box in a private message. I don't want the rest of them to be able to see it. I want a private message. Type them into the chat box. And I want everybody to respond. And if you don't know the answer, just type in, I don't know, IDK or whatever. And I'm not going to record your scores. There will be no penalty if you don't get them right. It's just that if we do this every day, hopefully as time goes on, you'll get more and more right as we go on. And then you'll score well in the test. Isaiah is asking if the test is in person or online, and the answer is it's online. Okay, so I want you to do this from memory. So please take your notes and set them aside, close them up, set them aside. I want you to be able to do this completely from memory. All righty, so here comes the first question on the quiz. Okay, all right. So I want you to tell me what is the nominal value of this resistor, and I also want you to tell me what is the maximum that it might possibly be. And I want you to do it from memory. Now, if you want to take a minute and write down on a piece of paper the little mnemonic, remember, bad boys race our young girls, but Violet generally wins. If you want to write that down real quick just to help you out, that certainly is allowed. Okay, so what is the nominal value? And what is the maximum that it might possibly be? Okay, I'm starting to see some answers. Now, rather than saying plus or minus what, I want you to actually calculate a number for what's the maximum that it might possibly be. Okay, I'm seeing some answers, and I'm seeing the same number repeated several times, but I'm also seeing a couple numbers that are different. And I'm seeing a couple of people admit that you don't know the answer, and then that's fine. There's no judgment here. If you don't answer, I am keeping track of who answers. Okay, so if you don't answer, then I will call you out. Okay. Now, some of you are putting numbers down without telling me whether it's the nominal or whether it's the maximum. So it would be good to specify what's the nominal value, what's the maximum value.
Are we doing the maximum or the?
I want you to tell me both. I want you to tell me what is the nominal and what is the maximum. Interesting. I am seeing the same number repeated several times, but not as often as I would like. I'm still seeing a fair number of numbers there that I suspect are not right. It looks like everybody has now answered or has admitted that you don't know the answer, and that's okay if you don't know. All right, let's see. Who was the first person that came in with an answer? All right, Caden, you were the first person that came in with an answer. Can you walk us through how you got your answer?
So it's like the color codes of like Gosh, I forget it exactly. I remember like the first part and then I fill in the rest just based
Okay.
on the rainbow.
Oh, you did the rainbow. Okay,
Yeah.
yeah, black, brown, and then RG-BIV.
Yeah.
That's a good way to do it. Yeah, I won't argue with that, but let's do it. Let's follow the mnemonic that they recommend in a lot of books here. So what I'm going to do is I'm going to put the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and then 9. Okay, so Caden, do you remember the mnemonic that we're supposed to, that some books recommend that you remember about bad boys?
Yeah, like it's like Bad Boys, like race something, but Violet always wins or something.
Okay, yeah,
I don't
so
know. I didn't memorize that one.
okay, imagine a bunch of little kids on tricycles. So get a picture in your mind, a bunch of little tiny kids on riding around on their tricycles, and you got these really bad boys, and they're convinced that they're going to win. And then this girl named Violet is the one that actually does win. Okay, so bad boys race our young girls, but Violet generally wins. Okay, so the first B is black. The second B is brown. And then the third B way down here, that one's blue. And the rest of them aren't a problem. Okay, so this first one is red. Caden, what number does that correspond to?
And that corresponds to 2.
Okay. Second one is blue. What does that correspond to?
6.
Okay. Third one is black. What does that correspond to?
0.
0. Now the fourth one is orange. What does that correspond to?
It means 3 zeros.
Okay, so it
Like 3 zeros at
corresponds
the
to
end.
number
Oh,
3.
put it in a suit with,
Yeah, yeah.
doing it.
So orange corresponds to number 3, but if it's the last one before we get to the tolerance band, we don't write a 3. What we do is we put 3 zeros. 1, 2, 3. Okay, so the nominal value is 260,000 ohms, or 260 kilo ohms. Okay, so that's good. All right, and now Caden, what about the tolerance band? What does silver correspond to?
Silver means plus or minus 10%.
Okay, plus or minus 10%. Okay, so 10% of 260,000, well, that's easy if you just move the decimal over. Okay, so that gives us, 2,000, or I'm sorry, 26,000. So if we just add those together, so what we'll get is 286,000 is the maximum that it might be, whereas 260,000, that's the nominal. Okay. All right. So this is something I guarantee they will ask several questions, or at least that I haven't actually seen the test. We teachers are not supposed to look at it. So I've just heard from other students who've taken it in previous years that the people who write these tests, they really like the color code here, and they ask several questions, making sure that you know how to use the color code. So every one of you, I expect you to be really good at the color code here. Okay, we'll move on to the next quiz question. So don't call it out loud, type it in the chat box in a private message. What does this schematic symbol represent? And it sounds like somebody's got their microphone on. I'm just going to go ahead and mute everybody here. Okay.
My bad.
Okay. All right. Okay, looks like most people have got an answer, and some of you have said that you don't know, and I appreciate your honesty there. Okay. And it looks like everybody has answered now. All right, Jasper, you were the first one to respond with an answer here. What do you think it is, and how do you know that?
It's a diode, and I guess I just know the symbol.
Yeah, you just kind of have to know it. All right. Okay, now if we were to hook it up to a battery and we want current to flow, how are we going to hook it up? So let's say here's my battery. I'm going to hook up this side to that side of the battery. And I'm going to hook up the other side through a resistor because I don't want to go burning anything out. Okay. All right. Now, should the right side of my battery be the positive side or should it be the negative side? Jasper, I want you to answer.
The left side should be negative and the other side should be positive.
So you're saying this should be the negative and this should be the positive.
Yeah.
Okay. How about the rest of you? You guys agree? Oh, we got some people here who are saying that they don't agree.
Is it the other way around?
Yeah, it is definitely the other way around. Okay. If you think of it like an arrow, okay, so this part of it here is an arrow and the arrowhead is pointing this way. So that tells you what direction the conventional current goes. And remember, we deal with conventional currents, even though we actually know now, we know now that what's really happening is the electrons are flowing the other direction. But still, I mean, back in the old days when they set it all up, they didn't know there were such things as electrons. And so what they decided was they were going to treat it as if the electricity flows from the plus side of the battery to the minus side. So if we hook it up like this through a resistor, okay, so electricity wants to flow this way. So if we hook up the diode this way, it will allow the electricity to flow through it and everything will be good. If we hook it up backwards, the diode is going to prevent electricity from flowing. Okay, so this symbol is definitely a diode and you absolutely need to know it because they will ask it on the question, ask it on the test. Now, I understand why it's confusing because there are several other symbols that all look very, very similar. They all have this triangle sign in them. And so I can understand why it would get a little bit confusing. So this one on the top here where it's got that vertical line there, or it's got that line, okay? So this is a diode. This other one here that's got the circle there, okay, that one is an inverter, or sometimes it's called a NOT gate. Okay, so this by itself is not normally just one electrical component. What you would have to do is you'd have to take a transistor and a resistor, and maybe in some cases a couple transistors, a couple resistors, and hook them up to give you this. Or if you want to buy an IC, an integrated circuit, you can buy an integrated circuit that'll do it for you. But I can understand why there's confusion because that inverter looks an awful lot like a diode. So the thing to look for is look for what do you see here? Do you see a circle there or do you see that line there? That's what tells you. And then to make things even more confusing, this other thing that's called an op amp, which is short for operational amplifier. Okay, and it's got that same triangle thing, but you can tell that this is not a diode or an inverter for a couple ways. One is you see that it has two inputs, and then also you've got this plus and minus V mark on here. So if you see those, then you know it's not a diode, it's not an inverter, you know it's an op amp. Okay, so just try and do what you have to remember these. You know that sheet that I gave you last time or a couple times ago that had the different symbols on it? I'd recommend that you print out that sheet and have that sheet by your side and just, before you go to bed every night, take a few minutes and review it. That'll really help you. Okay, next one. I want everybody to type in the chat box, what is this? Make sure you type it in a private message, not a public message. Now, this is a symbol that I don't think I've shown you before, but I have shown you the two pieces, and I'm thinking that you guys can figure it out. Okay, it looks like most of you are figuring it out. Let's get a few more people responding. Okay, all right. Okay, good. I think we have everybody responded now. That's a good guess there, Simon. Simon is suggesting it may be a broken battery, and I can understand that. Brian, can you tell us what your answer is and tell us why you think your answer is right? Earth calling Brian. Do you not have a microphone?
Oh, there it goes.
Okay.
Okay.
All right, gotcha.
So the reason why I think it's that, because usually when you have like a variable electrical component, there's going to be a line that goes through, like an arrow that goes through the circuit. Not
Okay,
circuit.
so if you've got a resistor here with an arrow going through it like that, that doesn't mean that it's a broken resistor. It means it's a variable resistor. It means it's got a knob on it or something where you can turn the knob so that it will adjust the amount of resistance. So you are exactly right in thinking that. Okay, so what we need to do is we need to look at this symbol right here and ask ourselves, what is that? So Brian, so this symbol that I just drew here, okay, what is that a symbol for?
It's a symbol for a battery.
Okay, that's a symbol for a battery. And it's a special kind of a battery. It's a multi-cell battery where you take like 2 batteries and you put them together, or maybe 3 batteries, put them together. Okay, so the underlying symbol there is clearly a symbol for a battery. So when we put the line on, or when we put the arrow on it like that, that's our way of saying that it's an adjustable voltage source. You could call it an adjustable battery, that would work. You remember the power supply? We did a bunch of things with the power supply. So, so the important thing here is that it's the type of current that we're going to get out of this is DC. Okay, so that means direct current. So it's the kind of current that a battery puts out. It's not like you get out of a wall. The electricity that comes out of a wall is what we call AC. And the symbol for an AC generator is this sinusoid. So if you get a circle with a little sinusoidal curve in it, that's AC. If you get a symbol like this, that means it's DC. So like the power supply that we used in Tinkercad many times, even though the power supply plugs into the wall, what it does is inside the power supply, it converts the AC electricity into DC electricity. And so it behaves as if it was a battery with a knob on it, where that you can get pretty much any voltage you want within the applicable range that it can handle. Okay, so good. Next one. Type into the chat box, what is this? Okay, I'm seeing a bunch of answers. All right. It looks like everybody has recognized that it is a logic gate of some sort. There seems to be some disagreement among you guys what kind of logic gate it is. It's almost half and half. More people are voting for an OR gate than AND gate, but there's a fair number of you who are thinking that it's an AND gate. But everybody's in agreement that it is definitely a logic gate. Okay, so you are correct, it is a logic gate, but it is not an AND gate, it is an OR gate. All right, so these are the most commonly used logic gates, not counting the NOT gate. Okay, and you need to know these shapes and you need to know them from memory. So the one on the left here, let me turn on annotation so I can draw it. Okay, so the one on the left here is an AND gate. And the one on the right is an AND gate with a little circle on the end. And that circle is an inverter. So if you take an AND gate and follow it by an inverter, what you'll get is what we call a NAND gate. So it's an AND gate, but then flipped, the output is flipped. Okay, so this next one down, so this is the one that I put on the previous page there. And so this one is definitely an OR gate. And so if we got the little circle on the end of it, that makes it be a NOR gate. Okay, now this one here is an OR gate with that extra little curvy part on the end. So what is that? Well, that's what we call an exclusive OR gate. And what that means is that the output will be high only if one of the inputs and only one of the inputs is high. Okay, if instead of having it like that, if we have both of the inputs be high, now, so with a regular OR gate, if both of your inputs are high, your output will be high. But with an exclusive OR gate, If both of your inputs are high, your output is going to be low. The only way you get a high output with an exclusive OR gate is if one and only one of the inputs is high. And so this is going to be an exclusive NOR gate, which is just an OR gate followed by an inverter. Okay, so make sure you know these shapes. This is AND, this is OR, and this is exclusive OR. And then if it's got a dot on the end, then you just stick an N in front of it. These are things that you need to know from memory to take the test that you will be taking very, very soon. I mean, January might seem like a long ways away, but remember, we got a 2-week Christmas break coming up, so it's not that much. Okay, so here we go. Here's our next one. Please type into the chat box telling me what you think this is. Okay, thank you for admitting that you don't know. That's good. Okay. Okay, so you guys have figured out that it has something to do with resistors, but it's a special kind of a resistor. And okay. All right, so one of you got the correct name. Now, several of you said it's a variable resistor, it's an adjustable resistor, which is correct. I wouldn't mark that wrong if you were to write that down. It does have a special name. Caden, what do you think the name of it is?
A potentiometer.
Yeah, potentiometer is the way that it's
potentiometer.
pronounced. But okay, so a potentiometer is in fact a variable resistor. And so what you do is you have your battery, which is, okay, so here's our battery over here. Whoops, let me try that again. Okay, so here's the battery, and we hook it up right here, and then we hook it up down here. And then now we have three terminals on this potentiometer. So this is terminal number 1. This is terminal number 2. This is a terminal as well. So if you were to pick up a potentiometer and look at it, you'd see 3 prongs coming out of it. Okay, so what we can do then is we can take this prong and then we can hook this up to whatever we want to hook it up to. Okay, and then so the voltage that we get here is going to depend on where we've got the dial set. So if we've got the dial set up here, then when the electricity flows through it, electricity flows through here. So you see it doesn't pass through very much of the resistor. So if we got it up here, this device down here is going to feel the full voltage of the battery. If on the other hand, we hang on a sec while I erase that. Okay, so if on the other hand we slide this the arrow down here, then the electricity that's flowing here is going to flow. It comes out here, and you can see how it has to go through a lot of the resistor before it finally gets down to here and comes into our device. And so because it went through so much resistance, the voltage is going to drop. So our device here is going to feel less voltage. So this kind of variable resistor where we have 3 terminals, that's called a potentiometer. Now there are other kinds of variable resistors. So the one that you see on the right here, okay, so this one is a variable resistor, but in this case, there are only 2 terminals. There's the in and then there's the out. There isn't this intermediate terminal like right here. So a rheostat is the name of a variable resistor that has only 2 terminals to it. A potentiometer is a variable resistor that has 3 terminals to it. So these are things that you guys need to know. And then you can see that there are also a couple other kinds of variable resistors. The one on the lower left here. So this one is a resistor where the amount of resistance you get depends on whether or not there's light falling on the resistor. The more light you have falling on the resistor, the less resistance it has. So that's called a photoresistor. And then this one right here, that symbol right there, that means it's a thermistor. And that's one where the amount of resistance that you get depends on the temperature. as the temperature changes, the amount of resistance that you're going to get changes. So those are 4 names that I want you guys to remember: potentiometer, rheostat, photoresistor, thermistor. Those are all variable resistors of different types. So be prepared that you might see those on the test in January. Okay, I just got a few more I want to go over. This is one that I've talked briefly about, only briefly, but let's see if you guys remember what it is. So go ahead and type it into the chat box. What do you think this thing is? Okay, it looks like some of you know. Okay, it looks like most of you are saying you don't know. And don't feel bad about that, because we really didn't talk about this very much. But some of you clearly do know. Okay, so those of you that put down an answer did say that it's a transistor of some type. And you are correct. It is definitely a transistor of some type. Okay, so now let's talk about if there are 2 general categories that the transistors can fall into. And in fact, let me just go ahead and let's go on to the next page here. Okay, so what you see here are a bunch of different transistors, and they fall into 2 general categories. The category on the right are called bipolar junction transistors, and the category on the left are called metal oxide field effect transistors, which I realize is a pretty big mouthful. So generally people just call them MOSFETs. And the ones on the right, those are quite often just called BJTs, bipolar junction transistors. Okay, so these are the 2 general types of families. Now, with a bipolar junction transistor, okay, they work based on current. So what I mean by that is, when we hook this up to our battery, so if this is the battery, okay, if we hook this up, we need to hook it up so that the plus side of the battery goes into this terminal right here, and then the negative side of the battery, and usually through some resistance, or well, actually, it doesn't have to be through some resistance. I mean, it could be, but it doesn't have to be. So the negative side of the battery goes to this terminal right here. Okay, now in order to turn on the resistor, because remember, I said transistor, I said resistor, I meant transistor. So in order to turn on a transistor, if it's a bipolar junction transistor, current has to actually flow into this terminal right here. If you don't have current coming into there, then the transistor is going to be in the off state. And so what you really want to do is you have like some really big battery here that's hooked up to a motor. And so you want the electricity to flow through here and then through the motor and then back into here. Okay. So what you have is a very weak signal here controlling a very strong signal here. Okay. And so if it's a bipolar junction transistor, current has to actually flow into the input terminal in order to turn it on. Now, if it's a MOSFET, things are different. You'll notice that this is our input terminal here, and you'll notice that there is no connection between the left side and the right side. There is no physical connection there. So current cannot flow into the transistor the way that it can with the BJT. But that's okay because it's designed differently. And I don't want to go into the details of how it's designed, mainly because you guys don't yet know enough physics in order to understand the details of how it works. You need to take my physics class, which I hope you will next year. When you take physics next year, we will talk about how it works. But for now, just take it on faith that, so if I take my battery here, if I connect my battery up like that, so electricity cannot flow into the transistor, but the fact that I've got it connected up to the plus side of the battery means that there will be a whole bunch of plus charges on here. And so even though current does not actually flow, that is enough so it can then turn on the transistor. So now the transistor will allow current to flow through it. Okay, so that's why we call it a field effect transistor, is because having all these plus charges here, it creates something that we call an electric field. And so the electric field is what turns on the transistor. Whereas over here, this is, if you wanted to, you could call this a current effect transistor. And in fact, that's what I wish they would have called it. I wish they would have called these field effect transistors, and they should have called these current effect transistors, and then it would have been less confusing. But unfortunately, they didn't ask me before they chose the names. We got to live with it. Okay, so now that we've done that, okay, so we've recognized now that we've got two general families of transistors, bipolar junctions and MOSFETs. Now the next question is we need to decide what kind of resistor it is. So if it's a bipolar junction transistor, you look for this arrow here, and that tells you whether it's a PNP or an NPN. Remember that arrow is effectively, it's a diode. Because with the bipolar junction transistor, I can't spell diode here. I'm trying to write while I'm thinking here, while I'm thinking about something else. Bipolar junction transistors are effectively just back-to-back diodes. That's how they work. Okay, so if we got a diode here, that means our other diode is going to be like that. And if we got a diode on the right side, that means our other one's here. And a diode, okay, always goes from positive to negative. So when I look at this diode right here, that's a PN junction. And that means this one's going to be PN. So you can see that if we start on this end and go through the diode, we hit the N first, and then we hit the P and the N. So that's why this is an NPN. But this one here, our diodes are reversed. So this is a PN diode. This is also a PN diode. So if we start at the top and go through it, we get PNP. So this is a PNP diode. This is an NPN diode. MOSFETs are very similar to that. Well, actually, before I talk about MOSFETs, I want to make sure you guys understand something about NPN and PNP transistors. The NPN transistor, that's the one that we worked with when we did all of our circuits, we made them. Okay, with an NPN transistor, what you want to do is you want to hook it up so that the plus side of the battery gets connected up to your input, and that will turn the resistor on. A PNP works backwards. With a PNP, what you need to do is you need to take your battery and you need to hook up the negative side of the battery to the input terminal there. And the plus side is what goes to here. So with an NPN transistor, in order to turn it on, you want to have the plus side of the battery on your input terminal. But with a PNP transistor, you want to do it the other way. With a PNP transistor, you want the negative side of the battery connected here, and that's what turns it on. So you see that they're complementary. Over here on the left side with our MOSFETs, if it's an NMOS transistor, it works the same way. If you connect the plus side of the battery to the transistor, then that will turn the transistor on so electricity can flow through it. If you've got a PMOS transistor, then you want to hook up the negative side of the battery. And you see on the upper symbol here how they've got that little dot there. That's their way of showing you. So if you were to take a plus charge here, and then this thing inverts it, so it makes it be negative. So being negative is what turns on a PMOS transistor, whereas being positive is what turns on an NMOS transistor. Okay. So I don't intend to go into any more detail other than that. Just you need to be aware, because I guarantee when you take the test in January, they're going to show you some symbols, and they might show you this symbol, they might show you this symbol, they might show you this symbol. You need to first of all recognize that it's a transistor, but that's by itself is not good enough. You need to also be able to identify whether it's a MOSFET or a BJT, and you need to be able to identify whether it's NPN, PNP, or if it's a MOSFET, you need to be able to identify whether it's NMOS or PMOS. So I would recommend that you look at this picture here, maybe take a screenshot of it or something, or on the study guide that I gave you. These are listed on the study guide. So just look at it there. Okay, we're almost finished with the quiz part, and then we'll start in on the new material. And actually, this is a good lead-in for the new material. Okay, so here is a symbol that I may have briefly mentioned once or twice, but only very, very briefly. And I would like you to go ahead and, yeah, okay, good. I see you're typing it in now. Okay, one of you definitely knows what it is. Okay, and several of you have a good idea of what it is. And those of you that don't know, thank you for being honest and admitting that you don't know. Okay. All right, good. So several of you have said that it's an inductor. You are correct, but it's a special kind of an inductor. And so, Brian, you were the first one that gave the fully correct answer. So Brian, can you unmute yourself and tell us, what did you call it?
I call it a transformer, but I'm not sure if that's an iron core or is that a ferrite core.
Uh-huh. Oh, wow. I'm impressed. Okay, it is definitely a transformer. So let's hold off on the core here. But yeah, it's definitely a transformer. So now some of you are going to say, what is a transformer? Well, a transformer is a thing that can change the voltage. It can either step the voltage up to a higher voltage, or it could step it down to a lower voltage. Now, transformers only work if you are dealing with alternating current. If you have direct current, transformers will not work. Now, you can do some tricks. You can take an induct. Well, actually, we're going to be talking later about some of the tricks. It is possible to take direct voltage, DC voltage, and it is possible to step it up to a higher voltage using something that's kind of sort of similar, okay, to a transformer, but you have to do some tricks with it. So let's set aside the tricks. So in this case, this is definitely a transformer. So what you can do is you can put in some low voltage, and then you can get out some high voltage. Or you can do it the other way around. You can put in high voltage and get out low voltage. Now, again, it's not my intention to spend time talking about how transformers work. That is not really the purpose of a beginning electronics class. That's more of an advanced thing. It's also physics. When you take physics, we'll talk in physics about how transistors work, or how transformers work and why they work. For all you need to know for this class is you just need to be able to recognize that it is in fact a transformer. Now, Brian was talking about there are different cores, there are different things that can go inside the transistor, right? So what you can do is you can put iron inside the core. You can put another material that's kind of like iron. It's called ferrite. Now, I do not anticipate that when you take the test in January that they're going to ask for that level of detail. I'm thinking that you just need to recognize that it is a transformer. Okay, so what we have here on the screen right now are several different varieties of transformers. The one on the top here, that's just a generic transformer. Now, a lot of times, that's the only symbol that people use, even if it is an iron core transformer, or I'm sorry, I said transformer. Let me back up. Okay, if you only see one of these squiggles, that by itself is not a transformer. If you only have one of these squiggles, that is something that we call an inductor. Okay, if you want to make a transformer, you have to take two inductors and set them side by side. So what we have on the bottom, okay, this part by itself is an inductor. This part here is a separate inductor, and they both share a common core. And so that if you take the two inductors together and have them share a common core, that is how you get a transformer. Okay. If you only have one coil, you do not have a transformer. What you have is an inductor. Okay. And so this is an iron core inductor. This one, I'm not completely sure if this is a ferrite core, because I know sometimes what they do is they have a symbol like this. So tell you what, let's not worry about the core. Let's not worry whether it's iron core or ferrite core. Just recognize that all of these are examples of different types of inductors. Now, I'm sure you guys can guess what's going on with this one. Isaiah, can you unmute yourself and tell me, what do you suppose this arrow through the inductor means? Do you have an
My
answer for this?
mind literally just went blank.
Okay, remember a
I-
few minutes.
I
Remember a
remember
few
you
minutes ago?
talking about it a few minutes ago when we were talking about the battery.
Yeah.
It is a multi-cell battery.
And then if we put that arrow through it, that means it's a variable voltage battery. And when we had a resistor, if we put the arrow through the resistor, that means it's a variable resistor. So what do you suppose is going to be the case if I take
Oh,
an
it's a
inductor?
variable inductor. Oh,
Yes, it's a variable inductor.
okay.
And then this one right here is also a variable inductor. It's very much like our potentiometer, where we had a resistor, where we have a third terminal that comes in here. So this is the exact same approach. So this on the left side is a variable inductor that has only 2 pins sticking out of it. And on the right side is a variable inductor that has 3 pins sticking out of it. Okay.
So
There-
the arrow pointing in, that isn't just for a different way how to write it. That means 3 pins and not 2.
Yes, it means 3 pins and not 2. Very good. Okay. All right. So now, I hope that you guys are sitting there right now saying, what in the world is an inductor? Because guess what is the topic for today's class? Inductors. Okay. We are going to learn what an inductor is and what it's used for, and what are some dangers that you have to deal with when you're working with inductors. But we're only going to superficially scratch the surface with inductors. Remember, this is a beginning electronics class, not an advanced electronics class. So all you guys need to do is you need to be able to recognize the symbol for an inductor. So on the test in January, if they give you this symbol and they ask you what it is, you just need to be able to recognize that that's an inductor. Even if you don't know what an inductor really is, just recognize that's the symbol for an inductor. But I do want you to know, at least in general terms, what an inductor is and what it does. Okay, so what we're going to do in order to learn a little bit more about inductors is I'm going to show you a video which I have put on Canvas. Now, I may not watch the entire video here. We'll see. So if you go to Canvas, if you click on the electronics page, and then you go to modules, and then you scroll down here. Okay, so you see that today's homework is inductors. So you click on that, and then I'll go here to preview so that what you see on the screen looks more like what you would actually see. Okay, so you'll see I have a couple videos here, actually 3. I have 3 videos that I think do a really good job of explaining what an inductor is. And so what I want you guys to do for your homework tonight is watch the videos, and then I have some questions down below that I want you to answer. But I want you to watch the videos first. I'm going to show you part of the first video because I think it does a really good job of explaining what inductors are. So I realize that when I show videos over Zoom, there's usually a lot of lag I apologize for the lag. I hope that it won't make it unintelligible. Okay, let's go. Let's see what we get.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at inductors to learn how they work, where we use them, and why they're important. Remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work.
Okay, I paused it just for a second, just because I want to make sure. Can you guys hear the sound? Somebody type in yes or no.
Yeah, we can
Okay,
hear it.
okay, good, because I know that sometimes the sound is a little bit goofy. All right, so I'll go ahead and restart the video. Pay close attention to this, guys.
So what is an inductor? An inductor is a component in an electrical circuit which stores energy in its magnetic field. It can release this energy almost instantly, and we'll see how it does that later on in this video. Being able to store and quickly release energy is a very important feature, and that's why we're going to use these in all sorts of circuits.
Again, I'm going to pause it for just a second. So when he talks about using it to store energy and then release it very, very quickly, a lot of you are saying, hey, wait a minute, that sounds an awful lot like a capacitor. Because remember, that's what capacitors did, right? They store energy and then they release it. The big difference is how the energy is stored. So hopefully when you guys took the quiz last time and I asked a quiz question where I said, how is the energy stored in a capacitor? The answer to that was it's stored in what we call the electric field. So in a capacitor, you have two plates. And when you charge up the one plate and you charge up the other plate opposite, what happens is in the region in between the two plates, we get something that's called an electric field, and energy is stored in that electric field in a capacitor. Well, with an inductor, it doesn't store the energy in an electric field. It stores it in a magnetic field, which we're going to learn more about right now. So we'll go ahead and restart the video.
Now, in our previous video, we looked at how capacitors work. Do check that out if you haven't already, links down below. So how does an inductor work? I want you to first think about water flowing through some pipes. There is a pump which pushes this water, and the pump is equivalent to our battery in the circuit. The pipe will split into two branches, and the pipes are equivalent to our wires. One branch has a pipe with a reducer in it, and that reduction makes it a little harder for water to flow through it. So the reducer is equivalent to resistance in our electrical circuit. The other branch has a water wheel built into it. The water wheel can rotate, and the water flowing through it will cause it to rotate. The wheel is very heavy though, so it takes some time to get it up to speed, and the water has to keep pushing against this to get it to move. This water wheel is going to be equivalent to our inductor. When we first start the pump, the water is going to flow, and it wants to get back to the pump as this is a closed loop. This is just like when electrons leave the battery, they flow and try and get back to the other side of the battery. By the way, in these animations, I use electron flow, which is from negative to positive, but you might be used to seeing conventional flow, which is from positive to negative. Just be aware of the two and which one we're using. So as the water flows, it reaches the branches and has to now decide which path to take. The water pushes against the wheel, but the wheel is going to take some time to get moving, and so it's adding a lot of resistance to the pipe, making it too difficult for the water to flow through this path. Therefore, the water will instead take the path of the reducer because it can flow straight through this and get back to the pump much easier. As the water keeps pushing, the wheel will begin to turn faster and faster until it reaches its maximum speed. Now, the wheel doesn't provide almost any resistance, so the water can flow through this path much easier than the path with the reducer in it. The water will pretty much stop flowing through the reducer, and it will all now flow through the water wheel. When we turn off the pump, no more water will enter the system, but the water wheel is going so fast it can't just stop, it has inertia.
Okay, so that's really important. Okay, so this wheel here, it's really heavy. So in order to get the wheel going, well, it takes a little bit of time. The water has to push on it for a long time. So at first, when we first turn on the pressure, Okay, the water tries to push the wheel, but because the wheel is so heavy, there's so much resistance that the water really can't flow through the wheel very well. So instead, it flows down through the lower branch. Okay, but as time goes on, this water wheel starts turning faster and faster and faster. And then once the water wheel gets up to full speed, now we're assuming this is a frictionless wheel. It has mass, but it has no friction. So once it gets up to speed, it now has what we call inertia. Boy, don't you wish you took physics? Boy, if you had taken physics prior to taking this class, that'd be a huge advantage. For some of you have. Okay, so the wheel now has lots of inertia. So once it has the inertia, then the water can go through there really well. And in fact, if we turn off the pump, because that wheel has so much inertia, it wants to keep going. And so it's going to keep pushing that water through, even though the pump is turned off. Okay, that wheel is going to keep on turning. And so it's going to keep the water flowing. And that's exactly what an inductor does. With an inductor, it's hard for the electricity to go through it at first. So the inductor provides a lot of resistance at first, but after a while, the current gets flowing through the inductor and it builds up a magnetic field. And then if we try to cut off the electricity, the inductor says, no, the inductor doesn't want the electricity to go off. And so it keeps it going. So let me just finish up this part of the video here. I'm gonna back up about 30 seconds so that you can hear this thing again, because this is the important part right here.
Water can flow through this path much easier than the path with the reducer in it. The water will pretty much stop flowing through the reducer and it will all now flow through the water wheel. When we turn off the pump, no more water will enter the system, but the water wheel is going so fast it can't just stop, it has inertia. As it keeps rotating, it will now push the water and act like a pump. The water will flow around the loop back on itself until the resistance in the pipes and the reducer slows the water down enough that the wheel stops spinning. We can therefore turn the pump on and off, and the water wheel will keep the water moving for a short duration during these interruptions. We get a very similar scenario when we connect an inductor in parallel with a resistive load such as a lamp. This is the same circuit as we just saw, but I've just wired it more neatly. When we power the circuit, the electrons are going to first flow through the lamp and power it. Very little current will flow through the inductor because of its resistance at first is too large. The resistance will reduce and allow more current to flow. Eventually, the inductor provides nearly no resistance, and so the electrons.
So notice that as the current through the inductor gets bigger and bigger, it builds up a magnetic field, and that magnetic field is where the energy is stored.
Electrons will prefer to take this path back to the power source rather than through the lamp, so the lamp will turn off. When we disconnect the power supply, the inductor is going to continue pushing electrons around in a loop and through the lamp until the resistance dissipates the energy. So what's happening in the inductor for it to act like this? Well, when we pass electrical current through a wire, the wire will generate a magnetic field around it. We can actually see this magnetic field by placing compasses around the wire. When we pass a current through the wire, the compasses will move and align with the magnetic field. When we reverse the direction of the current, the magnetic field reverses, and so the compasses will also reverse direction to align with this. The more current we pass through the wire, the larger the magnetic field becomes. When we wrap the wire into a coil, each wire again produces a magnetic field, but now it will all merge together and form one large, more powerful magnetic field. We can see that.
Okay, so there's more to the video here, but I think I'm going to stop it here. So having it in a coil makes the magnetic field be stronger. And if you really want it to be super strong, then what you do is you put an iron core inside of there. So let me turn on annotation here. So you may have heard me and Brian talking earlier about iron core. So if I just take the wire and I wrap it in a coil like this, I will get a magnet. But if I want a really, really strong magnet, what I should do is take some sort of an iron bar and stick it inside that coil. And that iron bar is going to make the magnetic field be even stronger still. And so then I can get a super strong magnetic field when the current is flowing. And so then I have an inductor that has a whole lot of inductance. So let's talk a little bit about inductance right now. So let's suppose that at first I have a coil without the magnetic field inside. So it's going to be a pretty good inductor, but it's not going to be as strong as it could be otherwise. So if I were to measure how much inductance it is, and let's say I come up with some number, let's say that it's 420 whatever units it is we use to measure inductance in. Well, that thing that we measure inductance in is called a Henry. Okay, so 420 millihenries, that would be the unit that we use for inductance. So if I take this same inductor, but I then put a magnetic core inside of it, then all of a sudden my inductance goes way up. So in fact, it goes so high that maybe I'm not even going to measure it in millihenries anymore. I'm going to start measuring it in actual henries. So now I'm up to like maybe 15 henries or maybe 24 henries. Okay. So with an inductive core, I can get a whole lot of inductance. I'm sorry, with the iron core, I can get a lot of inductance, which means I get a lot of henries. And without the iron core, well, I still get some inductance, but it's going to be so small that I'm going to probably have to measure it in millihenries, maybe even microhenries, depending on how big the coil is. Okay. All right, now, there's one thing about this video that I'm not especially happy with. Let me come back to this part right here. In fact, let me even move it a little bit more to, how about, okay, so right here. What he says in this video is that when we turn off the pump, okay, so the water is no longer flowing here, okay, the wheel keeps turning. And so the wheel is going to keep pushing the electricity. And now in this case, we've got a loop here so that as the wheel turns, the electricity can just flow through this loop. If we didn't have this branch right here, we would have a very interesting problem. This wheel here is trying to push the water, but if we don't have this feedback loop here, the water is trying to go out here and it tries to go into the pump, but the pump is turned off. So what's going to happen is we're going to build up a lot of pressure here. And now here is where the video does something that isn't completely right. The way that this is explained, it sounds like the amount of pressure that you get from the wheel is going to be equal to the pressure that you got from the pump. But the real world is different than that. If this was a real inductor, then, and so let's hang on a sec here. So let's take it to this picture. Okay, right here. Okay, so this inductor that you see right here is kind of like the wheel. So when we get current flowing through here, if we all of a sudden open up the switch to cut off the electricity, so the inductor wants to keep the electricity flowing, the inductor is going to create the electrical equivalent of pressure. And hopefully you guys realize that the electrical equivalent of pressure is what we call voltage. But here's the important thing. With an inductor, the voltage that you get when you cut off the switch can be way higher than the original voltage was. So let's suppose this is a 9-volt battery. And so we use this 9-volt battery to get this current flowing through the inductor. So we build up a magnetic field around the inductor. when we close the switch, this inductor gives voltage, but this voltage here can be way higher than 9 volts. This voltage here could be 100 volts, 200 volts, 300 volts. Okay. And his little analogy here where he uses the water wheel, you know, that doesn't it doesn't quite match the reality. Have any of you guys taken an auto mechanics class? So type into the chat box yes or no if you've either taken an auto mechanics class or had a little experience. Okay, so it looks like Brian has taken one. So if you took an automobile class, then you have learned about spark plugs and how spark plugs work. So this is one application of an inductor. Let me open up a whiteboard here. Okay. In your car, you have a 12-volt battery. And so let's say here's the plus side, here's the minus side. So when you're driving your car, this 12-volt battery is used to charge up an inductor. Okay. And so you get current flowing through this inductor. And so because the current is flowing through the inductor, that builds up a magnetic field right here. Okay. And then when you need a spark, what happens is that you temporarily cut the current here, and this inductor says, "Whoa, I don't like the current being cut," and so it builds up a current, a voltage in it that tries to keep the current going, and the voltage here can be much, much, much higher than 12 volts. It can be like 100 volts or 200 volts or 300 volts. And so over here, if you have your spark plug, you know, so here is the spark plug, and it's got a piece up here, and then it's got a little piece right there. Okay, so this is made out of metal, and this is metal, and the rest of it down here is all an insulator. Okay. When you cut the voltage here, the coil, the inductor, it builds up what we call flyback voltage. So that flyback voltage can be way higher than the battery that initially started it. And so the voltage gets to be so great that then what can happen is you get a spark right here. And so that's how you run the spark plug in your car, is because of the voltage that comes from an inductor. And so we call this flyback voltage. Okay. All right, so flyback voltage can be very, very high. And in fact, flyback voltage can be so high that it can damage your circuit if you're not careful. So let me show you an example of something here. Okay, so these are pictures of inductors, and you can see that they come in several different sizes, but generally, you know, you can easily recognize an inductor because it's a coil here. Okay, and so if you have some sort of a circuit that has an inductor in it, then you have to be very careful, because when you cut the current on the inductor here, when you open up the switch here, this inductor is going to give you a tremendous amount of flyback voltage. And so the voltage could be really high, so that whatever device it is that you have here, remember the R that you see in a circuit, that doesn't necessarily mean it's a resistor that you know, like the kind you see in Tinkercad. This could be anything that uses electricity. This could be your phone. Let's say you want to charge your phone, or maybe it's a computer you're using to power your computer. Okay, when you open up the switch here, you get a huge spike of voltage that we call flyback voltage. And that flyback voltage could be so high that you destroy your computer or your phone or whatever. So what we want to do is we put a diode in here that's called a flyback diode, so that when we get this huge voltage here, the electricity can go through this feedback path here. And so that you can, it lets the electricity flow without damaging your phone. So a flyback diode is a very important thing to include in your circuit if you have an inductor in your circuit. Now, some of you might say, well, if inductors can potentially damage your circuit, let's just not use inductors in our circuit unless we really, really need it. Well, I got bad news for you. A lot of things that people need to use on an everyday basis actually have inductors built into them. One very common one is an electric motor. What you see here is a picture of an electric motor with the cover taken off of it. So if you look inside the electric motor, you'll see all of these coils. That's how motors work. If you didn't have those coils, the motor would not work. So whenever you have a circuit that has a motor in it, you've got an inductor. Whether you like it or not, you've got an inductor. And so you had better put a flyback diode into your circuit, because otherwise when you cut the power to your motor, you're going to get flyback voltage that can damage other things that are in the circuit. But if you put a flyback diode in place there, then when you cut off the power to your motor, then the electricity can flow through the flyback diode and it won't damage anything. Okay, so I realize that I have not really explained very much about why people want to use inductors. I've just told you that if you have a motor, you have an inductor, whether you like it or not. Well, there actually are cases where inductors are really useful. But in order to fully understand how it works, I would have to teach you a bunch of physics that you don't yet know. Let me just tell you in words what are some things that the inductors are useful for. Even though we're not going to talk in detail about how it works, I'll just tell you what they're used for. Inductors are used when you have a bunch of alternating current frequencies, like radios. That's a great example of an inductor. When you take the radio and you turn it on and you want to listen to some station, and if you look at, and let me draw a picture here so I can show it a little bit better. Okay, so here is your radio, and here's the radio antenna, and here's the dial on the radio, so you can set it to whatever. So let's suppose that the radio station you want to listen to is 88.9 on your FM dial. Okay, that 88.9, that tells you the frequency of the radio station. Okay, so what's happening is that there's a radio station somewhere and it's broadcasting signals that have a frequency of 88.9. But there are other radio stations, other places that are also broadcasting radio stations that have a different frequency. Okay. And so, I mean, here in Salt Lake, there are dozens of different radio stations. They're all broadcasting at the same time. And when you pick up your radio, all of these different frequencies, they're all being picked up by the antenna. What you want to do is you want to filter out all of these other frequencies. You want to somehow block the other frequencies, and you only want to listen to that one frequency. So what are you going to use? An inductor, okay? And I'm not going to take the time to explain how you do it because I would need to teach you a whole bunch of physics first. So take my physics class, take honors physics, and we'll talk about it then. But basically an inductor is what lets you filter out the unwanted frequencies and amplify the frequency that you do want. That's what inductors are used for. Okay, so I have now told you everything that I expect you to learn about in related to inductors in this class. So Tristan just sent me a question. He's saying, he wants to know if he'll learn about that in the U of U class. And the answer is yes, Tristan, in about 2 months from now, Dr. Panzeris is going to spend at least a good week teaching you all about inductors, and you're going to understand then really well how inductors work. Okay, so when you guys take this state mandated test in January, they're not going to ask you how to calculate what size of inductor you need for a particular application. That's beyond the scope of this class. But what they will do is they might ask you to say, name something that an inductor is used for. Or they might ask you, what units are used when you're measuring how much inductance an inductor has? And so you need to know the answer to that is Henry's. And you need to know that the applications for inductors are like spark plugs, to power the spark plug in a car, to tune in on a particular radio frequency and block out the other frequencies and only amplify the frequency that you want. Those are the kinds of things that I expect you to know. Okay, so that's pretty much it for today. And it looks like that's good because we're out of time. All right, so there is going to be a quiz for today. If you paid attention, then you'll find that the quiz questions are going to be pretty easy to answer. But I would recommend that you watch the videos here. So on my page in Canvas, where the quiz questions are, there are 3 videos. I highly recommend that you watch all 3 of the videos, but I don't require you to watch all 3 of them. But I would hope that you'd be interested enough that you'd want to. Okay, I'm going to call it quits. If you don't have any questions, you can type bye into the chat box and head out. If you do have a question, I'll gladly take your questions right now. And if you want me to stop the recording so that you can ask a question without it being recorded, I'll do that right now.